Okay, so first thing I want to describe to you about this week is we use a lot of terminology this week that has to do with the normal curve. And your normal curve is basically the bell curve. And what you need to know about it is that basically a long time ago, after a lot of study, people realized that when you have randomly selected data, it very often falls into this normal curve distribution. And what happens is within the normal curve, there is the average, that's x bar, and that ends up at the middle. That's the mean. Then, as you get further and further out to the edges, you have one standard deviation above the mean. So that's x bar plus one standard deviation. Hang on, let me just fix this here. So we've got x bar plus one standard deviation. This like circle with a hat on it, this thing right here, that's standard deviation. That's a sigma. So I have x bar plus one standard deviation. I have x bar plus two standard deviations. And then out here is even more stuff. And then when you go in the other direction, you have x bar minus one standard deviation and x bar minus two standard deviations. So that's basically how all of those things work. And then what you read beyond that is we started talking about confidence intervals and hypothesis testing. And basically what you figure out is that when you take a sample, the average of that sample is this x bar. Okay, that's the average of your sample. And then what we decide to make beyond that is we make a confidence interval. And that confidence interval says, well, if this is your sample, and that's your sample average, if you want to find 95% of the time, find a range that will give you the true average. So instead of just sampling your people, you sampled everybody, making it a population. If you want to find the true average, it's somewhere in between two standard deviations below the mean and two standard deviations above the mean. Okay, so long story short, that's how you get a confidence interval. You take your sample mean, you add two standard deviations, you subtract two standard deviations, and then you get a confidence interval. So let me give you an example over here. So let's say here's a scenario for you. 5 years ago, it was stated that the mean starting salary of a nurse in the greater Rochester area was, say, $36,000. We think, in fact we hope, that the standard average salary for first-year nurses has risen since that time. But we're not quite sure. We think it has, but if we want to prove it, we need to collect data to prove it. Now, one way to prove it would be to get every nurse in the greater Rochester area that's a first-year nurse and get all of their different salaries and then look at the average and say, yep, the average went up, the average went down. But obviously, that's unrealistic. I can't look at data for every nurse in the greater Rochester area. So instead, what we have to do is we have to sample nurses and say, all right, I got this small set. Here's what their average is. Does that show enough that it has risen or not? So if we look over here, I've got 30 sample salaries right here. So I've got people at 43,000, that's definitely above, but 28,000 is below. Here's somebody at 31, here's somebody at 33. So I'm not really sure by looking at this if the average is greater than 36,000. Okay, and then you may say, well, maybe I could like sort the data. And again, you don't need to know how to do the sorting stuff. I'm just going to do it for you here. So I just want to sort the data. I clicked on the wrong thing, pardon me. I just want to sort the data. And now if I look at it sorted, I've got 22,000, 25,000. 36,000 is right here at person number 11, and then everybody beyond that is above 36,000. So that might, but also might not, mean that the average salary has gone up. I'm still not sure, okay? So what do we do statistically to be sure? Well, what we do is we take our sample group, okay, and in that sample group, I'm going to come over here and go to data analysis. Again, you don't need to know how to do this. You go to data analysis, descriptive statistics. I take my input from column A. It has a label. I'm going to put an output right here so I can look at what it tells me. And summary statistics and confidence level for mean, I'm going to make a 95% confidence level here. So I've got to go to 95%. And here are the descriptive statistics for the sample salaries. So what does all this information tell me? Well, it tells me that the average salary is now $40,566. Well, that average is greater than 36,000, but this is just a sample. How do I know that maybe I didn't miss some home health aid visiting nurse service company that pays their employees, nonsense? So I have to realize that I don't have everybody in this sample. So this number alone isn't enough to tell me whether or not it's gone up or down. The only way to know that is to get a confidence interval, and that range will say, okay, I got an average of $40,566. But there's got to be an error, a give or take. So to make a confidence interval, what I'm going to do over here is I am going to take this mean value right here and what's called the confidence confidence level value down here, and I'm going to add and subtract them. So to find the confidence interval, I am going to take my mean value, which was up here, 4556, no, 4566. So 4566, and then I need to subtract the confidence level value, this 4142. And again, I'm just using the whole numbers. And I also need to add those two numbers together. So 4556 plus 42. And if I do that, pardon me, I will use a little calculator over here. I know I have one on here. Come here. I don't know where it is on this computer. So I'm going to let Excel do it for me. I can make Excel do stuff for me. It's pretty cool. I can tell Excel, hey, I want you to take 4566 and subtract 4142. And I want you to take 4566 and add 4142. So the new range is 36,424 to 44,708. 36,424. And what was this one? 44,708. All right. After watching me do a bunch of stuff on Excel that I told you don't need to know how to do, but I wanted you to see me do it, after watching all of that, now I have a confidence interval. And my confidence interval for all of that information is now, I can say with 95% confidence that the true population mean for first year nurses' salaries is somewhere between $36,424 and $44,708. That's what I just did. By finding the mean and the confidence level and adding and subtracting them, I get a window. And that window tells me that even though I have a sample mean of about $40,000, the true population mean isn't going to be exactly the same. It's going to be somewhere between these other two numbers. Now, the question was, has that shown that the average salary has increased beyond this 36,000? Well, since I'm 95% confident that the real salary is between 36,424 and 44,708, I can say, you know what? Yes, I am confident that this value has gone up. So I can now say, since the confidence interval has values that are all above $36,000, we do have evidence to show that the average salary has risen. Okay? Now, here's the tricksy part. We have evidence, and actually, we have evidence at the 97.5% level. Whoa, where did that number come from? Well, it's a little weird, but basically that number came from the fact that when we looked at this, that's not what I wanted to happen. Come on, draw. Nope, it doesn't want to draw. Sorry, I'm working through this as we talk here. When we look at this chart right here, this purple region that we talked about, this is 95%, which means that I've got 2.5% down here and 2.5% up here. If all I care about is the fact that I'm above 36,000, that would start here and go up. Well, if there's 2.5% here, there's a 97.5% up there. I know that's a little confusing, but I just wanted to show you that technically when you use a 95% confidence level, you're really getting a 97.5% confidence that you have increased your value. Now I'm going to talk about that a little more in the next example, so just bear with me for a minute here. Okay, so now the next thing I want to do is go through your homework examples, all right? So here's an example that's almost identical to question 1 on your homework. So if you can follow me through this, then when you go to do your homework, it should be exactly the same process, only with different values, okay? So what I gave you here in my sheet is we have a list of cholesterols, okay? And what we want to know is this data, is this cholesterol data that we have here, is this data normally distributed or not? Okay, so something that's normally distributed, you read about, has to fall into that normal curve. It has to look like a bell curve, okay? The other thing you can say about it is when something is normally distributed, the mean, the median, and the mode are all equal to each other, okay, or close to it. Your cumulative percentages have to match or be close to these theoretical percentages, and the histogram has to look like a bell curve, okay? So we're going to go through and talk about whether or not this data is normally distributed. So look at the gray box, compare the mean, the median, and the mode. So the mean is 285.1. The median is 276, and the mode is 273. Those aren't really that close. Maybe if it stayed in the 280s overall, I'd say okay, or all in the 270s, but those are pretty different. So I'm going to say, since the mean and the median are, how far apart are those? Are 9 apart, and the mean and the mode are 12 apart, these values aren't close enough together to show a normal distribution. Now let's pretend I didn't have that information. Part B says look at the blue box. So all we care about is the blue box. Compare the cumulative frequencies to the theoretical frequencies. Theoreticals are the normal ones. Do these indicate normal distribution? So I've got 0.5% in 2, 15.5 and 16, 57 and 50, 84, 84, 96 and a half, 98, 100, 100. Those actually look okay. I mean, they're not perfect, but you're rarely going to get a perfectly normal distribution. So I would say, since the percentages are relatively close to the theoretical percentages, I would say that there's a chance the data is normally distributed. All right, and last but not least, examine the histogram that was created using the standard deviation bins. Does it indicate the data are approximately distributed? So if something's normally distributed, I want to look at this and I want to see a nice bell. I want to be able to fold it in half and have the two halves lie on top of each other. And there is just no way that's going to happen. When I fold this in half, along like this line right here, there's no way. These don't really even come close to folding on top of each other. So that is not a normally distributed histogram. It's just not going to happen. So since the histogram is not symmetric, this doesn't appear to be normally distributed. So what would the final conclusion be? I would conclude that this data is not normally distributed because we looked at 3 different views of the data, meaning we looked at the percentage view, we looked at the histogram view, and we looked at the mean, median, and mode view. When we looked at 3 different views of the data, 2 out of the 3 indicated otherwise. Okay? Now, this is kind of an iffy area. It's a gray area. Statistics is not an exact science. That's why we're only 95% sure of something. So when you talk about these things, if you give me an answer that's not exactly what I was looking for, but you can back it up with information, even if I disagree with your answer, if your information and your backup is okay, that's fine with me. What I want to know is, are you comparing the frequencies? Are you comparing the mean, median, and mode? And then describing things based on that. Okay, so now let's look at example 2. Again, this is just like what you have to do in your homework, only it's using different numbers. So let's say, I'm looking at this cholesterol data, and somebody told me that the mean cholesterol for adults is 290. Can this claim be justified or rejected at the 5% level of significance using the data? So, in other words, people think that the mean cholesterol is 290. I don't know what people, I'm just making this up, but let's say somebody tells me that the average cholesterol is 290. Can I justify that or can I reject that? Now, when you're talking about justifying or rejecting a claim, meaning you want to say, yes, this person's right or no, this person's wrong, what we do instead of just a confidence interval is we do a hypothesis test using a confidence interval, okay? So if I am testing a claim, we need to state 2 hypotheses. So my one hypothesis is H sub O, the other one is H sub 1. H sub O means the null hypothesis. And I have a silly little rhyme for this. H sub O is the status quo. In other words, H sub O is what you're given. It's what somebody told you it's supposed to be. It's the average that's generally accepted, whatever. H sub O is status quo. And that is going to be, in this case, that the mean cholesterol for adults is 290. H sub 1 is what you're testing against. H sub 1 is the opposite of H sub O. So H sub O is status quo. H sub 1 is, well, I think that's wrong. So if mean cholesterol for adults is 290, if that's HO, H1 is mean cholesterol is not 290. Okay? So those are my hypotheses. Next, we state the significance level. This will always be significance level is going to be 5%. No matter what, our significance level is going to be 5%, which is equal to 0.05. That will be important later. All right, now which box, blue or gray? Well, all I have is the gray box. Let me quickly make a blue box, and I'll explain why in a second here. So you can ignore what I'm doing. Just pretend you don't need to know this at all, because you really don't. This happens behind the scenes. C 23. All right, and we'll make this guy blue. Okay, so which box am I going to use, the blue box or the gray box? Okay, well, I have a significance level of 5%. I want to see if there is a change in cholesterol, 290 versus not 290. So all I'm trying to say is, yes, you're right, or no, you're wrong. But I don't care which way. I don't care if the average cholesterol went up versus if it went down. Either way is fine with me. So when that's the case, you want to use a 95% confidence level. Here, I'll change it to red. Whenever you don't care in either direction if something goes up or goes down, you're going to use the 95% confidence level box. So whatever box I give you, you want to find the one that says 95%. If instead I said that mean cholesterol is 290, and here's a group of people who exercise a lot, and they think their mean cholesterol is less than 290, We still use a 5% level of significance, but we have to use a 90% confidence level in Excel. I will explain that in a moment. You don't care about it right now, just trust me. So if it's change versus no change, 95%. If it's increase or decrease, then you want to use 90%, okay? So which box? We want the gray box because we're looking for a difference or a change instead of a specific increase or decrease. Okay? All right, next, state the confidence interval used. So if I want to state the confidence interval that was used, a confidence interval, we learned in the last workbook, or worksheet, pardon me, the confidence interval is when you add the mean and the confidence level and subtract the mean and the confidence level. So my mean was 285 and my confidence level was 9. So 285 plus 9, 285 minus 9. So let's see, 285 minus 9 is going to be 276 and 285 plus 9 is going to be 294. So the confidence interval is 276 to 294. What does that mean again? Well, it means that even though the average for the group that I'm studying has a cholesterol of 285, that's a sample. So with that sample, I can really only say that I think the population's cholesterol is between 276 and 294. I'm not quite sure. So it's claimed that the mean cholesterol is 290. Is 290 in this interval? Yes, it is. So since 290 is within the interval, we have to support the null hypothesis that the average cholesterol is 290. And last but not least with this, I spelled cholesterol wrong. And last but not least with this, what kind of error might we have made? Now this error thing in classifying it, there's type 1 errors and type 2 errors. A type 1 error is when you reject the null hypothesis, except it's actually true. And a type 2 error is when you accept the null hypothesis, even though it's false. So we supported the null hypothesis, which means that our possible error is a type 2 error because we accepted the null hypothesis, even though there's a possibility that it's false. Now, what is the possibility that it's false? 5%. There's a 5% chance we're wrong. And you know what? We're willing to live with that. Now, when the drug companies are testing drugs, they work with a much higher level of confidence than 95%, but they use all of this. And I can absolutely guarantee it. My father works for a pharmaceutical company, and he does quality control for blood analyzers and injectables. And I think they work with 99% in a lot of their cases. And when you talk about the drugs and the drugs entering the body and that part of everything, I think they use even higher than that. So they do not want to make any mistakes. We're working with 95% now, but again, depending on the stakes, they might use a higher percentage. Okay? All right, I know we're at 23 minutes right now, which is a long time to be listening to a video. Just hang tight. I've got one more example, and hopefully we will put all your minds at ease. All right, so our last example is the same type of thing. All right, here's the systolic blood pressure of a whole group of people. All right, and it's known in the past that average systolic blood pressure was assumed to be at most 115. I just made this up, okay? I'm just putting some information out there. Let's say for a certain group of people, they averaged a systolic blood pressure of at most 115. It's now speculated that there's been an increase in systolic blood pressure. So let's say, we looked at people's systolic blood pressure before they entered boot camp or something like that for the Army. And then we looked at their systolic blood pressure after leaving boot camp, and we think, you know what? I think going through all that really raises their blood pressure, and we want to check it out. So this, let's say, is their like new systolic blood pressure. We want to know if it's increased. So using the data, can it be justified at a 5% level of significance that there has been an increase? Okay, so state the null and the alternative hypothesis. So H sub O is the status quo. H sub O is what you have been told. So H sub O is that average systolic blood pressure is at most 115. H sub 1 is what we're testing for, and we think average systolic blood pressure has increased above 115, so more than 115. Okay? State the significance level. It is always 5%. Which box, blue or gray, and why? All right, so blue versus gray and why. If you are looking for an increase, not a change, not it went up, maybe it went down, don't care which way. If you are looking for an increase specifically or a decrease specifically, you want to use the box that has a 90% confidence level. Let me take 2 seconds to explain that to you. The reason being is you want to look at the fact that I have this normal curve, okay? Here's my mean, okay? If I want 95% of the data, I want to show that there has been an increase beyond a certain value. So if that value is down here, and I want 95% of my data to be above it, that means, pardon me, that I want 5% of my data to be below it. Well, if I want 5% to be below it, Excel only works in symmetry. So when Excel says 90% confidence, Excel means that the middle part is 90%, leaving 5% on either side. So when we are looking for a specific increase, I don't care about that. I only care about this. And I have to trick Excel into giving me this by saying I want a 90% interval. If what I just said doesn't make any sense, doesn't matter, don't worry about it. I take care of all of it for you. Excel takes care of all of it for you. All I need you to know is that if it says increase, or alternatively decrease, you want to find the box that says 90%. Okay? So which box, blue or gray, and why? We want to use the blue box because it's the 90% confidence box, which gives us 5% on one tail. Okay? So 90% confidence whenever we're doing a strict increase or a decrease. All right, state the confidence interval. So we're using the blue box, so we're going to completely ignore the gray box. So in the blue box, to get a confidence interval, I take the mean and add or subtract the confidence level. So my mean is 121.6, and then I'm going to add and subtract. I put a little plus minus there if you can see it. I'm going to add and subtract 1.95. And you can make Excel do this for you if you want by just typing it in here with an equals 121.6 plus 1.95 and 121.6 minus 1.95. So my confidence interval is 119.65 to 123.55. All right, what was I testing? I want to see if we have increased beyond 115. Is 115 in this interval? No, no it is not. So state my conclusion. Since 115 is not in the confidence interval, then we reject our null hypothesis and support our alternative hypothesis. In other words, we have evidence to suggest that systolic blood pressure has increased beyond 115. All right, and what type of error is this? Error depends on whether you rejected or supported the null hypothesis. We rejected the null hypothesis, so type 1 error is possible because we rejected H sub O, and there's a small chance that it's actually true. Again, what small chance? 5%. Type 1 error. Okay? So I hope this helped a little bit. I know this is the first video, so it was a little rough. I do need to make this a little bit more polished, but I wanted to have you hear my voice and feel like, okay, somebody's with me, somebody's walking through this with me. So hopefully this made you all feel like I'm standing there by your side. Do your best, email me, call me with any questions you might have. And I really like jokes. This is a strange thing about me. I really like jokes. And one of my favorite jokes is a pirate joke. And the pirate joke is this: what has 8 eyes and 8 legs? 8 pirates. Think about it. Think about it. Oh, there it is. You see it. You see it now. And my other favorite joke, if you have small children, they will like this too. Why don't you ever see elephants hiding in trees? Because they're really good at it. All right, I hope you got a laugh and a chuckle at the end of what was 30 minutes of math. Enjoy yourselves, take a breather, go eat a cookie. That would be my favorite, and we will chat again soon.